All right, let's find the derivative using the limit definition of the derivative, right? It's the limit of the slopes of secant lines, turning those secant lines into a tangent line. So f prime of x, the derivative is by definition the limit as the distance, or h we'll call it, goes to 0 of my function at a point x plus that distance h minus f of x, right? That's my change in my y values. And then over x plus h minus x, the change in the x values, which will just be an h, right? That's h, that distance. Now I'm looking at this distance, the slopes of the secant lines. As h goes to 0, that turns into a tangent line. Okay. So let's apply this to our function. My function is the x squared function. So this will be x plus h squared. All right, limit as h goes to 0. Let's see what we can do here, right? Because I can't directly substitute just yet. If I did, h would be 0, and then that term would look like that term if h went to 0. So I'd have 0 over 0 indeterminate. But let's simplify. I can rewrite x plus h squared as x plus 2xh plus h squared. Through simplification, my x squareds are gone. I now have 2xh plus h squared over h. Everything in my numerator has an h in it. Let's pull that out. 2x plus h. And there's our cancellation. Ooh, bad limit. Limit as h goes to 0 of 2x plus h. Now that I've performed that cancellation, I now have no problem directly substituting. If I send h to 0, this becomes 2x. Now notice your derivative depends on x. Right, there's an x right there. So your derivative depends on x. So it's going to change, right? The slope of this function is going to change depending on where we look at it. So I want to graph both of these. Let's remind ourselves. The derivative of this function was found to be 2x. If we were to graph these, that's my y-axis where we'll plot the function values, the x-axis. Now our original function, x squared, was the concave up parabola, right, sitting right there at the origin, symmetric over the y-axis. In fact, let me label this. This is x squared. Our derivative, let's put this in green, is the function 2x, right? The straight line with slope 2, y-intercept 0. All right, so let's pick a point. Let's look at maybe 3. Now, if I evaluate my original function at 3, that's 3 squared, gives me 9. So this point right here is the y value 9. If I was to evaluate my derivative at that same point, 3, then that is 2x, so 2 times 3, it gives me a 6. So the value of my derivative, ooh, I did not draw this right. Let me fix this. My derivative is much more steep. Or rather, my original function is much more steep. My derivative is much more shallow. All right. Now, my original function returned a value of 9. My derivative at 3 returned a value of 6. That's better. So what this means is the slope of that tangent line right there, right? The tangent line to my function at the point 3 has a slope equal to the value of the derivative at 3, right? That's what the derivative is. It's a function whose outputs are the slopes of the tangent lines. So the slope of that red line right there is 6.